So good afternoon. Today we'll be having a discussion on GIS data models. So in this lectures, basic objective is to find out, or the learning objective is to understand the importance of data structure in GIS analysis. Then we will also look into how does the spatial relationship are basically presented. So there are different spatial relationship, how it is represented. That's what we'll discuss. Then we'll also see the basic data structure which is being used in GIS. Mostly we'll be restricting our discussions to just 2D data structures. Then the most models which is being used to represent the data, GIS data, is raster and vector data sets. So we'll be seeing how the data sets actually get represented in raster and vector format, and basically their uses, few of the area uses, and different formats, how it is being used, that also we'll see. And then we'll also explore few of the open standards which is being used for representing this different spatial data models. So we'll be concluding with a set of examples of GIS data format which is currently is being used. So we'll look into all these till the at the end of this whole sessions. We should be able to explain what exactly, why do we need a GIS data structures. Then we should be also able to understand what's the difference between raster and vector data types. And then we'll see basically the spatial relationships and their topological relationship, how it is getting represented. So what exactly is the meaning of the topological relationship, that also we'll explore. And then we'll see the few of the side effects if you go from vector to raster data format. So what are the effects, and in those cases what needs to be taken care of, and the corresponding quality assessments things also we'll just briefly discuss. Then we'll see a few of the examples which you should be able to explain and see that if somebody talks about a HTTP file or maybe a GeoPackage file format, so you should be able to understand what exactly is the underlying data models in which these data sets are stored. So we'll see the Open Geospatial Data Consortium based, that is the OGC format, data based and different data models. So let's take a basic overview of what exactly is the GIS. So in GIS, generally there will be a few user requirements. So as you can see in this, the user requirement is just to find a distances or the path between place A to place B. So we'll try to find out what exactly is the different path which is available if we want to go from place A to place B. So if you want to solve these problems, as we can see that the features which is present on the earth and which is being represented as a satellite imagery is quite complex. So there are trees, there are houses, there are roads, there are buildings, and a lot of other structures, spatial structures which is present on the ground. So what we do is we extract only the important informations which is present in reality in form of certain data models, so that the different type of GIS analysis can be carried out. So that's in this case we need to just extract the different road networks and the places where these road networks are interconnecting those nodes, and the path needs to be found out, so that we should be able to answer a query which is being given to find out a path from A to B. Similar kind of problems we can have in larger domain as well. So like there may be a problems or related to ecological analysis, cultural analysis, there may be a hazard based analysis, and as well as different network and connections as well. So in this case, we are observing that we need to find out multiple solutions from the same real world by extracting the certain informations. So for that, we have to do some kind of organizations of the data so that the user requirements or specifications can be mapped to specific use case, maybe related to finding out path, maybe some ecological problems, and so on. So for that, we have to look for somehow to organize that data sets. So those data sets may be in form of databases or in form of files and so on. Then what we do is we execute these models, or these there are different processing models according to the problems in a specific environment, using certain functionalities. For example, let's say if in the examples which we just discussed, that we need to find out the path from A to B. So to find the path, there has to be a certain algorithms which needs to be executed, and that's what we do as a part of GIS analysis, where these data sets, whatever data which we have taken, that will, and the organized data sets goes as an input, and then finally we get an output in form of the shortest path. So it gives you a kind of a subset of a set of edges or nodes. If you put them in a sequence, then you will be able to create a path. So that actually is a part of functionality which takes those data as an input. And then finally in GIS uses, what we do is we give or we whatever output is getting generated through certain functional capabilities, what we do is we do and represent it back to the user. So the output may be in form of map visualizations and so on, or it may be in form of instructions. So you may be aware of the certain instructions which you get it in your map services through Google Map and so on. So there will be one person key which may be involved and giving you continuous basically the instructions. So as a part of GIS, if you see, the overall workflow requires that you need to have certain uses or a kind of specific requirements that has to be mapped into a certain mathematical and conceptual models, and then finally we do certain amounts of evaluations. So for using these models and usage, which may be an iterative as a part of the iterative process, the first step required is a kind of data organizations. So if you just zoom in to the first problem again, so from that perspective, if we take it, the basic GIS requirement is finding a shortest path. So and that's what as a human being will be interested in. So you don't bother about what exactly goes in your Google Maps. You simply type in the to and from two places, and finally you get an output that gets generated in form of maps. So the GIS basically gives you the whatever the requirements are there, the user requirement that gets converted into a very GIS specific questions, that is finding a shortest path. So that may be the GIS questions, which may be further elaborated in terms of specific algorithms and so on, that can get executed as a part of GIS process and models, and finally you get a solutions as a part of answers. So to do this, the data organization is the basic fundamental part, and that's what we will be discussing and trying to understand how exactly in the machine, the data which is there in a very complex reality form, how it is being organized. So let's take questions or the informations which is present to find this path from place A to place B. So this is just a simple query which as an requirement is to find a distance from a place A, that is the Indian Institute of Remote Sensing, and there is one of the important place of Dehradun which is called a clock towers. So these two are the places in which we have to find it out the path. So to find out this path, if even if you don't have any machines or you are not using any GIS solutions, if you want to find out this particular path, then you need to ask a few questions to, or maybe you can ask someone who will guide you that how can you reach clock tower from a IIRS. So during their explanations, they will use a certain names. Like in this case, there's a Kalidas Road, and they will understand that an Institute of Remote Sensing is located at Kalidas Roads, which is connected to Rajpur Road through New Kent Road, and then we can get a connectivity from IIRS to Rajpur Road. That information is available. So these informations, whatever informations we have, if we try to put this whole informations to a machines, then we have to do a certain organization. So generally, whenever we say data organizations, as a part of your to get an output as a part of any analysis, to find out basically giving a statement by some human based analysis, they will be telling you, or somebody may tell you that you can reach from IRS to basically Ghantagar through via Kalidas Road and New Kent Road, and some of them may give you a certain additional informations like it may take 10 to 12 to 14 minutes. So in this case, all these analysis requires a basic informations, which is where exactly is the IRS, their geography, the different connectivities, and so on. That is basically the kind of information which the person should know, and then only on the basis of that and or having an understanding of a geography, they will be able to guide you and give you the suggestions. Now, if you want to do same analysis using machine data sets, so then we have to see what are the information which is available. Like in this case, place A is locations, which is IRS. Then B is also a locations. There are connectivity to that locations to specific road, which is the Kalidas roads. And then there are multiple roads which are connected, like Rajpur Road and Chakrata Road. They are connected at the junctions. And then finally, different then again, New Kent Road is also connected. So this is basically trying to explain that there are certain connectivities which is required between different paths along with the different locations. But if you want to you convert these particular informations into a machine so that it can execute, then we have to look for certain commonalities of such information from very vast set of similar kind of informations. So the way we are interested in finding out a problem under this problem, that we want to go from location A IRS to clock tower. Similarly, some other persons may be interested in going some other places, maybe clock tower to ISBT and so on. So there will be a certain similar kind of informations which will be available. So in that case, what we have to do is we have to take these machine data sets and then these informations, and then we have to look for the common properties of similar kind of informations, and then we organize these data set as a part of your machines. For example, in this case, the A and B is having an location, so that can be represented as a point geometry, and it is having a name, so that name is the part of it which should be stored in a machine data sets. Then we also know that each of these point geometry is also having a kind of latitude and longitude, because as we are telling a point geometry, so it needs to have a certain location. So these are basically locations of both the places, and their latitude and longitude are there, which needs to be stored as a part of point geometry. Along with that, there are other elements which is required to do this analysis, which is roads, and roads are nothing but a simple line segments or a line geometry which is consists of a lot of multiple segments, because road cannot be a kind of straight lines. It may be consist of multiple segments, and all of them segments connected together, we call it a line geometry, and that needs to be that will be common across similar kind of informations. Then to give you a better result or maybe as an outcome of your analysis result, you need to know how much time does it takes to hop from one end to the another end of a specific road segment. So it means that each of the road segments we need to have a certain travel time available. Like for example, in New Can Road it may take 3 minutes. For Rajpur Road and at 7 minutes you have to travel, and then on Kallas Road you need to travel around 2 minutes. So all these information has to be there, or will be organized as a part of your machine data sets. So once you put it all these in a proper structured format, then we call it as a data structure. So as a part of machine based organizations of all these informations on a common structure is called a data structures, and that once we are able to organize them, then definitely we can call it certain GIS functionality to give you the result as an output of maybe in terms of giving some numbers that how to reach and what is the total time it will take from going from one place to the another places. It may also give you distance as a part of it. So if you see in details, there are machine data is having a certain geometrical properties, which is locations, and these locations when you connect, then you get a lot of segments. With segments again, when you connect it, you get a line geometry. So all these are actually a geometrical property. So line, point, all these are a part, or we can call it a geometrical properties. And along with that, there are certain additional information which may be required as a part of your solutions. For example, travel time is required to give you exact time you need to spend to go from place A to place B. Or it may also have an information like name, which can tell you that which may be used in during the map display or during the annotations and so on. So these informations, combining both of them together, has to be put it in a common structure format, which we call it a machine data sets. So this shows that a common informations or similar kind of information have a certain commonalities, which you group them together as a part of geometrical and attribute data sets to solve the GIS problems. So that was the part which is related to line and points. Similarly, you can have a certain aerial phenomenon as well. For example, land covers, like in this map, you're seeing that there are a lot of forest areas are there. So all these forest area are actually continuously distributed in a extent or geographical areas. There are also non-forest areas and so on. So it's basically features are actually spread spatially, and those features are actually continuous in representations. I mean, they are having a continuity. There's no gap in between whenever we say as a part of any aerial phenomenon. While in the case of roads are discrete because it takes one space and there are different places. So these line, or in other word, we can say the line geometries are actually the discrete objects, and there may be empty spaces between them, where in case of aerial phenomenon you can have a continuously wide area spread, and you can convert, or you can just partitions the whole area in terms of different features like forest, non-forest, and water bodies and so on. So generally, there's other way of telling that the different aerial phenomenon or object-based representation will have a very sharp, crisp boundaries. For example, the admin boundaries are a kind of sharp and crisp boundaries, which can tell that these polygons basically represents the state of Uttarakhand. But there are certain aerial features which is continuous in domain, continuous, which is basically, for example, terrain slope is not going to change. So means they are continuous, spread spatially, and there is a no break available. So these features are actually called field based features, and generally we represent them in a form of grid or a digital elevation models. So let's see the examples of how the features actually gets represented in discrete object format or in form of grid-based systems. So in case of this is just an examples where you are having a line which is represented in a green color. You're having a point at the top, and then you're also having a polygons. So the same features which is being represented in two different way. One is that it is a geometry which is consist of a set of line segments, and closing the line segment or joining the start and end point, you will get a kind of polygons. And then there are also a point which will have a certain coordinate systems. That basically is the representation of vector format. So vector format basically consists of set of data points, and each of the data points will have corresponding latitude and longitude, or maybe the coordinate systems associated with that will be stored for each and every points. And then what we do is we do take a sequence of those points, connect them, we create a segments, and then finally if we have a closed segments, then we call it as a polygon. Similar kind of features can also be represented in a gridded format. So as you can see, the polygons which is in a red color is being shown in the gridded format on the right hand side with a green color and having an attribute 2. So these two numbers basically tells that this is a polygon in a raster data sets. Similarly, we are having a line, and the line is being represented as a continuous connection of multiple cells. So that's what we see it over here, that the line segments belongs to a certain grid or a cell, and where through all the cells which is through which the actual physical line is traversing, you are just connecting them together and you are creating a line. So in these two are basically a vector or raster data representations, and as you can see, depending upon the kind of representations, the output in terms of representation looks quite different. So you're in a vector, you have the geometry intact, where in case of raster, it no longer remains a line, but rather than a filled box or a cell. So this is just an example of how your geographical features may be represented in two different formats. To represent those gridded format, we need to have an location and spatial reference systems. So that spatial reference systems basically gives you the coordinate system. So if you look at the shape of the Earth, it is not spheroid, it is very uneven shapes, and it is you can think of the shape is like a potato. So there may be a certain places which will be high rise, there will be certain places on the Earth which will be a low area compared to the normal surfaces. So this is the actual shape of the Earth. So what we do is we have to have the coordinates with a specific reference system, so that whenever we say point, the corresponding coordinate systems can be assigned. So for that, we need to have a spatial referencing systems, and that spatial referencing system is basically related to first geometrical or the simplified mathematical approximations, which is being done in terms of spheroid. So spheroid is very similar to sphere, but slightly oblated in one of the axes you can think of. So that first you have to have a kind of mathematical approximation of the shape, so that it covers the the surfaces of a spheroid at least touches or do basically represents the different shape of the Earth. Then what we do, this is a 3D features. So what we have to do, we have to reproject them on 2D plane. So for that we have a certain projection system. So one is when you do a representation in form of 3D shapes, this is called datum. So finally this datum has to be represented in 2D form, which is a projected systems. So as a part of the projected systems, if you try to put it any 3D objects in 2D plane, they are bound to be having certain distortions. In some cases, area may be distorted. In some cases, the distances between 2 points, which is actually on the 3D space, may be distorted, and so on. So depending upon the type of compromise which you can make, the corresponding projection systems can be created. So once you select the projection systems, then what happens, each of these spatial features which is in 2D dimension or in 3D dimension, that's the spheroid based locations, that gets projected on a 2D systems. So to minimize the distortions that may be in terms of shapes or which may be in terms of distance. There are different ways of selecting the spheroid. So spheroid basically makes sure that the shapes or the 3D shape which you select in such a way that whatever the error which is there in a local reference plane. So let's say we are interested only in the projected system around the India and surrounding regions. So we don't bother about if there is any large differences which may be possible from 2D, 3D systems to the 2D projection system, let's say in the US or maybe in Europe. So in that case, what we can do, we can select certain parameters for spheroid creations that we call it a local spheroid, and corresponding local referencing planes can be created. That's why we have a kind of Everest projection systems and so on, which basically ensures that if you have any kind of distortion between actual Earth and the spheroid, that should be minimum. And then finally, when you are doing a local spheroid projections back into plane, there is also a minimum distortion. So you are as near to the measurement or actual measurement as possible. That's the basic objective of the local GIS spatial reference system. So all these information, like which spheroid you have selected, what kind of projection system which you have chosen, combined together actually gives you the coordinate systems. And within these coordinate systems, you do representation of the different features as we have seen in the previous slide. So let's see the as a part of machine data organizations. So whatever we had earlier, the map data gets projected, or the raster or vector data formats actually is a part of map data projections. And then you have additional geometrical properties which can be stored in form of tin. So tin you can think of 2D representations, but through using certain computations we can arrive and we can create a 3D surfaces. So all these are actually a map data representations, and then you combine them with the attributes like travel time or the names and so on. And then you can also have some additional relationship among these attributes and the corresponding geometrical data as a part of your databases. So generally the databases actually maintains the geometrical relationships and the attribute relationships, combine them together, so that whenever you want to make any query, or you want to just click on a particular polygon and you want to find out what's name or what's the area, the corresponding relationship can be extracted. So that can be stored as a part of your relational databases. So in the nowadays, you can also store the raster data sets, which is nothing but a kind of image data format that can be stored as a part of your machine data organizations. So we'll see a few of the examples of how it is getting represented. So whenever we say spatial data sets, so as a part of your geometry, you have three major geometry, which is point, line, and polygon. So you can say that polygon is a special case of line where the starting and end points actually is the same. So if you create or construct a line, if you have a starting and end point to be the same locations, then you get a polygon. So you create geometrical properties or geometrical data sets, and then you also stores the attribute data sets separately and put them in a form of with the combinations of GIS data sets. As we have discussed that to find out the path or locations or give any points corresponding latitude and longitude or some coordinate systems, you need to also have a certain auxiliary informations related to coordinate systems. So these coordinate systems, as we have seen earlier, that may be related to local reference plane or maybe global reference plane, depending upon the kind of your uses. You select those auxiliary systems or auxiliary projection systems that is required for doing analysis further. maybe representing the data sets, maybe computing the distances, maybe doing some kind of GIS analysis and so on. All these are additional information which machine data needs to store it as a part of your different data structures. So let's see that how exactly these data sets or exactly these data formats looks like in a projection system. So this is just an example of few point line polygons and corresponding representation of that data sets along with the kin representation, which is nothing but a set of triangulated irregular network. So this gets created using certain algorithms to show that the height attributes can be extracted from them, and that's basically Delancey triangle based algorithm is being executed so that you get a when you execute and when you appropriately project these triangles, then you will be able to recover back the 3D or tin information. So these are basically a geometrical attribute or map data format which is possible in GIS systems. So let's now slightly dive into more detail that how this raster or vector data set is storing the information. So this is just an example of raster data sets. So as you can see, this is having a certain row and column numbers. But if you look at closely or very carefully, the actual location is considered to be centered at the cell. So that's the first important point which you have to keep in your mind, that as a part of raster coordinate systems, any locations is a representation of center of that grid or that cell, particular cell. For example, one cell at 1 comma 1 will be the first topmost left grid or left cell. If somebody is giving you latitude, longitude values from the raster data sets, so this will basically represent the center of that cell. So that's the general representation of any kind of raster data format. So if you look at, if you see these structures very carefully, so you can understand that there's no continuity of the point representation in the raster data format. Raster data formats are always discrete in nature. So they will be represented with one point and there will be an unique distances or very unique cell distances where the next point will be placed. So those points can be placed on the left or the top or maybe bottom or maybe on a corner side, but each of them will be having one cell distances. So that's the first things which we have to understand, that in the raster data sets, the point representation is not continuous in nature. So the impact of that is any points which you want to represent in a raster coordinate systems, you cannot have fraction values. So the result of that is that there is already an uncertainty related to one point locations within, which is equivalent to at max the half of the diagonal distance. So that is one root, basically it's a half of the diagonal distance. So if you are having a row and column of equal length, so half of that diagonal distance or root 2 times by half, that is, if you take a cell size of 10 meters, so 10 by root 2 will be the distances where uncertainty is already built in. Even if at a point is very near to on the top corner of 1 comma 1, but just slowly or less just below the top line, the automatically that value will be considered to be located at the center of 1 comma 1. So that immediately creates a kind of uncertainty which you have to keep in your mind. Then in case of raster data structures, what another important point is that each of the features or the attribute value will be stored at a locations, and in a raster data sets you can store at max only a single attribute. So each of those values, like in this case, as you can see in the 6 comma 8 or the 6th row and 8th column, there's a value stored is 46, and this raster grid is going to represent only one particular attribute that is called 46. So this 46 may represent a radiance, or it may also represents the height, or it may represents the any other outcome of certain raster analysis. But the important point to be noted here is that in raster you can store at max only a single values. You can stack such a multiple grid together and you can create a stacked layer. So then you will be able to get or gauge in the multiple attribute values. So means if you have 10 attributes, then corresponding 10 similar grid structure needs to be created, and each of these grid structures has to be filled with the corresponding attribute values. So the like in this case you are having an coordinate at 5 8 comma 6, the value is stored at 6, and this may be considered as a functional output. So generally any field data sets which is continuous in nature like terrain or temperature will be stored in this format, where the important point to be noted here is that the structure of these cells are fixed. So means at the beginning itself you know which particular point is neighbor to whom and what is the distances between those neighbor points. So this is well known at the beginning of itself. So means this spatial structure grid is fixed and the value is stored at the attributes, and the topological relationship is also fixed. So whenever we say topological relationships, so it's basically you can think of that the neighbor relationship, how one cell is related to the next cell. So that cell may be on the left side, maybe top side, maybe bottom, maybe top corner, right, maybe at the corner, top corner or bottom corner, and so on. So in case of raster data structures, such topological relationship among the points are fixed. So if you want to, let's say if you want to move from 8 comma 6, from there if you want to find out who is the left neighbor, you simply needs to subtract the row values. If you want to go the top, you need to subtract the one value from the column number, you'll be able to reach to the top. So means you are already having an understanding of who is your neighbor as a part of your grid structure, which is having a fixed topological relationship. So that's why in a raster data, the topology building and such kind of exercise is not required, but in case of vector, we need to have it. And the values generally in a raster data set gets represented only when you have at least half of that feature is covering the or half of the area of the cell is being covered by a features. So this becomes an important considerations while you're doing an rasterizations. So if you look into the overall structures, there may be a certain uncertainties which may arise. For example, let's say if this grid size of 25 kilometers, like IMD data sets, which gives you a rainfall of every 25 kilometers grid data set. That's the generally available data set which is available. So what it means is that anywhere within the cell of 25 by 25, whatever value, rain value you may be having actual rain values, finally the positions will be at the center of that grid size. So it means there is already a positional uncertainty that you have to keep in your mind. And you can store it only a single values, which is the rainfall. You cannot store the temperature and so on. For that you have to have a separate grid structures or grid coordinate system attached to it. As the regularity of these points are fixed, so means each of the points and their distances are well known, so you don't need to georeference each and every point. So the impact of that is that you need to just store the one of the corner points, that top may be of the origin latitude and longitude values may be stored, and then if you want to find out what's the corresponding center value of, let's say 1 comma 2 or first row second column, then you need to just add the two or 1.5 cell distances to that origin, and you will be able to get the x direction changes, and the y direction you have to just make a half pixel distances. So means that each of the points whatever is being represented over here are not going to have a latitude or longitude or maybe any kind of reference coordinate systems that can be computed on the fly with using the what's the origin coordinate values and what's the grid distances. If you use these two, then using the row column formula, you can easily compute the coordinate system. But as a part of your data structure, that particular value is not getting stored. Where in case of vector data sets, you have to store those value as well. The important another important concepts which we have to understand in case of spatial relationship is that there's something called topologies, which is important from the perspective of vector data sets. So as in the previous slide we discussed, and we saw that in case of raster data sets, the spatial properties of the different grids are already fixed and they are well known, where in case of vector data sets you may be having a multiple relationships, or there might be a relationship which has to be defined appropriately as a part of your topological data structures. For example, in this case, the topological relationship is that one of the polygon is actually inside the another polygon. So D is the basically the outer polygon, or E is the inner polygon. So E is inside the D. So this is basically a topological relationship. Similarly, you can have a neighborhood relationship, so like the state relationship. So whatever you do, whatever transformation or representation of the state of one state, if you do it, the relationship between the one state and the neighboring state is not going to change, even be it on the 2D representation or 3D representation. So this is basically another properties of the topological relationship, that under different type of transformations, the relative relationship between neighbors are not going to change, and that will remain fixed. So this is very important from point of GIS analysis, because there may be a certain cases where topological analysis or topological relationship may be required. For example, let's say that you're having a road, and there might be a requirement to do a widening of that road, but that road is just beside a river stream. So means there is only possibility of creating a buffer only in one direction. So in that case, if we have to do how much area you have to take from the one side or opposite side of the river stream, in that case what you have to do is you have to know that there is a river which is on the on left or right side of the road. So in that area or that particular reasons, you cannot do additional extension of the road. So it means that additional buffer cannot be created. So the corresponding analysis has to be carried out on the other side. So in this case, the direction becomes an important part, and you have to have if you're looking for a real life analysis, then in those cases the topological relationship actually becomes important, and that basically increases or enhances your geospatial analysis. Then they also help in to find out certain queries, like for example, somebody may be interested that which parcel is, or which particular piece of land is left or right side, which is at the center, or such kind of things queries can be do. So it means like wherever we look for a spatial relationship, in those cases the topological relationship is required as a for carrying out the GIS analysis. And it also enables you to create an consistency in your data set. So as you're having an topological data sets, so even if there's a change in boundary shift, it is not going to happen in such a way that you'll be having an empty space in between. So the topological basic relationship ensures that if there's a contractions in one of the adjacent edge, the one of the edges of any polygons, the other polygons get stretched so that there is no gap. If you're not having a topological data sets, then what may happen is there may be a kind of duplicacy in a common areas. For example, in this case, the polygon on the green and yellow, even if somebody has digitized it perfectly, but both of them will be having one extra common edges which will be present. Apart from that, there are also certain errors, like in this case, as you can see at the border, there are edges which is supposed to be a single one, but there are a kind of overlapping edges. So this is basically happening due to non-topological relationship which is existing, and this gets generated during the digitizations or data generation stage, where the editing is not being done with appropriate topological enabled editing is not being done. The result of that is there will be dispute at the borders. In some cases, there may be under and overestimations that may also be possible in case of topological, if your data sets are not properly or not having a proper topological relationships. So you need to have vectored models which basically takes care of these topological models. So generally there are 4 different type of relationship which it should be able to store or preserve, so that if any topological analysis is required, that these properties can be exploited for the analysis. So one is adjacency, it's basically finding out who is neighbor to whom. Then there is a connectivity, so which particular grid, grid or polygons are actually connected, so that connectivity is there. Then containment, especially if you're having one polygon inside the another polygons to find out island areas, so that 2 of these features can be considered separately. Those are the containment. And then coincidence, basically the 2 shapes sharing the same area. So few of these there are few ways of representing these topological relationships. Like in this case, you're having a certain lines, polygons. So as you can see, the whole rectangular area has been divided into multiple polygons, and each of those polygons is having certain number of edges. Like in this case, for example, the left topmost polygon, which is number 9, is actually having an line which is 1, 5 and 6. So if you put it in appropriate order, then you'll be able to get an area which is bounded by line 5. So as a part of topological relationship, what happens is that you store the relationship between each lines, and then you also store which particular polygon is on left and right. So for example, as you can see, the line number 6 is actually adjacent to polygon 2 and polygon 5. So the line number 6 on the left hand side. So how do we decide which is the left and right? So as you can see from the arrow, so arrow directions you have to face it, and then accordingly you have to place your hand. So on the left and right side, you can see the polygon 2 is on the left hand side of that edge 6, and polygon 5 is on the right hand of the edge. So these relationship has to be stored as a part of your topological relationship, apart from the set of sequence of points and corresponding lines that needs to be stored if any kind of topological relationship has to be stored as a part of your GIS data structures. So these are the other relationships. The similar kind of relationship is like disjoint, meet, equal, and inside. So very similar to your one is connectivity, another is one is meeting or not meeting. On the basis of that, you are having disjoint and meet. Meet is maybe having a sharing of single point, or they may share also a edge or line, or there may be an equal, or this is basically a coincidence, which is 2 polygons sharing the boundary or area, both of them equally. So those are equals. Inside are, there is one particular polygon is inside the other polygons, and there is a no common point or line which is between inner and outer boundary. So those are actually not there. So this kind of relationship can be created in form of spatial relationships. These are the spatial relationship which has to be stored in as a part of your topological relationships. So in nutshell, what we can say is the topological relationships are nothing but a set of transformations which is not going to change, a set of relationship which is not going to change under any kind of transformations. So as you can see, this is a simple example of paper piece, which is, you can see that polygon A, B, C marked on the right top. That piece of origami paper is, even if you fold it, the portions which will be represented on the final bird shape, the relationship between A, B, C will remain same. So in the 3D conversions also, or 3D transformations also, the A will remain to the left side of the polygon B, and C will remain on the right side of the polygon B, and this relationship is existing. Similarly, the north-west direction relationships are also can be there. So we can say that the Uttar Pradesh, or maybe the Uttarakhand, is actually to the north of Uttar Pradesh, and so on. So those kind of spatial relationship will be preserved, and those kind of topological relationship will be there. So these are the common format which is getting stored, like this is the ARC data format, or you can say this is basically the ArcGIS specific format, where polygons are line being stored. And then you also have another file structure which stores the each of the points and the corresponding relationship of those points as a part of any line segment, which is called arc. So file 3 in this case basically stores the starting and ending nodes and intermediate nodes. So that's if you traverse it from the starting node, that the first node, and the terminating node, you'll get a sequence, and that sequence path is called arc. And then you're having a polygons, each of those polygons and their topological relationship as a left and right is being stored as a part of your arc file format, and this is also called E00 format, which is being stored. So as we can say that the vector data models are object-based models, so means you'll be having a very crisp boundaries, maybe at a point, line, and polygons, where raster data sets are actually full area field cover data formats. Then in case of vectors, the point fractions can be represented. So means the coordinate systems can have some fraction values, where in case of raster, you cannot have fraction values. You have to have a row and column numbers. And accordingly, the intermediate spaces cannot be represented in a raster data format. It takes less spaces because the information which is being needs to be stored only for specific features, where in case of raster data sets, even if there's a no feature available at any places, you have to use very specific value that is called NA value or no data values that will be stored. So whatever software which is going to interpret that particular cell, and if it is finds any specific values, so it understands that this needs to be interpreted as no values. But no values also needs to be stored, which is that's why we have a very large raster files compared to the vector data sets. And the vector data models are basically geometrical objects. So you will be having point, line, and polygons, and that's the basic objects, where in case of raster, the smallest unit is actually a cell that gets stored. The analysis which needs to be carried out in a vector is actually a geometrical analysis. So means if you're trying to find out, let's say, two polygon on their common area, so there has to be a geometrical solutions or algorithms would be able to handle the geometry of two polygons, and on the basis of that you'll be able to find out the common area. Where in case of raster, basically the grid structures are fixed and they have to be aligned. So once they are fixed and aligned, their size and their extents are fixed, then you just need to do some kind of algebraic manipulations, addition, subtractions, and so on. In case of vector datasets, each points are referenced. In case of raster datasets, only the referencing has to be for the original cell values, and rest all of them is going to be computed with the help of row and column numbers. So these are the few data formats like E0, KML, and so on. Those are actually vector data formats. The raster data format are imagery format like GeoTIFF, IMG, and so on. This slides basically talks about the effect of if you have any kind of vector data sets, and if you just do a conversion from vector to a raster data sets, which may be required under certain GIS analysis, because certain GIS software or algorithms may work on a raster data structures and they may not work on a vector data sets. For example, the extraction of different features or the road extraction from satellite imagery. So you may be having a straight lines or the road network, which is as a geometrical straight lines, but in the imagery, those straight lines will be rasterized. So if you're looking, if you're creating some kind of algorithms which will trying to find out whatever vector data or road network is there and corresponding raster images, then you need to do some kind of rasterization. So during the rasterization process, what happens is that the geometrical properties, which is straight lines property or the way the smoothness of the curve actually get lost. So it is clear from the on the right side, as you see the lines which are supposed to be smooth, but after the rasterizations it gets staggered effect, or there's a staircase effect gets generated, and the smoothness is no longer as what you as it can be observed in the vector data sets. The other issue is that, as I had said earlier, that any vector data sets, if has to be represented in a grid structures, it needs to occupy at least half of the pixel area. So the impact of that is the linear features like river or road networks, and if you're rasterizing them, and if any sections of the road which may be passing through a cell but may not be enough to fill the 50% of the area, then that particular grid will be assigned to the majority class values. The result of that is there will be a kind of discontinuity. So the impact of that may be in the analysis. For example, if you're doing some hydrological analysis, so on the vector data set, you may see a road network or maybe a river channel, but in the rasterized output, there may be a certain gaps which may get created because at certain narrow channel spaces, the width was not enough to fill the half of the pixel areas. So these pitfall you have to be aware of, along with the uncertainty in the spaces which is possible. This is just an example of tin models, which is also storing the XY coordinate and Z coordinate for the values. The important point over here to be noted is that the XY are actually a geometrical coordinate which gets stored, and Z coordinate is actually stored as an attribute separately. So this has to be stored, or this is basically an assignment of property or Z properties to each of the point locations, and then you create or you have two separate lists or two separate files which may be a collections of triangles, and giving you which all basically is the triangles. This is part of which all adjacent triangles. So this is topological relationship. For example, in the edges table, as you can see, the triangle A is actually adjacent to the triangle B and K, leaving apart from the external triangles. That is also been, you can think of that is also there. Then you will be having nodes. So each triangles and what are their node number and the corresponding node, then and their latitude and longitude is value is being stored in a node list. So if you combine all of them together, so you'll be able to create a tin topological relationships. So it's basically a 3D models, which is triangulated based. You can see triangulated based models or algorithms basically is being used, and using the interpolations method, you can compute the height at different locations. In GIS, there are certain data formats which is quite useful, or which is basically present everywhere. So the vector file formats are like GeoJSON, KML, and shapefiles, which are quite dominant. In the raster file format, there is grid file, GeoTIFF, and JPEG 2000 file format, and so on. Then there are other way of storing the GIS data format is maybe as a part of databases, which has certain spatial extensions apart from the basic databases functionalities. Like in case of Postgres, you have PostGIS. If you have these PostGIS additional package installed on the Postgres, then you can use the geodatabases. You can use them, or the Postgres databases. You can use them as a geodatabases. The remote sensing data formats are LIDAR, LAS, and other formats are also there. Then if you want to deal with the WebGIS domain, then the data which works is, or the standard which is being used is WCS, WFS, and so on. So probably you'll be coming to know these data formats also. So these are the additional data format which is present. Nowadays you have a geotagged images. So as a part of your image, you store certain latitude and longitude. Apart from that, the unstructured like your tutes or something may have a certain additional tag which can be attached to a location references, and that can be used for further analysis. There are other 3D file formats which we haven't discussed, but that is still existing in a geospatial domain, and that may be used in a different 3D related projects and analysis. And then there are certain projects file which is specific to a software, like in QGIS you have a QGIS, which is nothing but a set of metadata or informations about the different files, and their locations is being stored, not actual data sets, but their location information is being stored in these project file format. So let's take an example of geodatabase, which is popularly which is basically popularly available in commercial software like ArcGIS. So we call it, they call it as in personal geodatabases. So inside the personal geodatabases, you may be having a set of feature data sets. So its feature data sets are nothing but it stores a common auxiliary information about the coordinate system, units, and so on. And these common feature data sets, within this auxiliary information, you can have point line and polygons which that can be stored as a part of your spatial personal geodatabases. Personal geospatial databases can also store the raster data set. So as you can see, the height is which is a kind of gridded structure, is a kind of TIFF images that is being stored. Then you may be having certain additional very specific data structures related to network analysis. So this is related to this is required for solving the problems at the beginning, the way we had to find out the shortest path from one locations to another locations. So all these point line polygon has to be converted into network data structures so that the shortest path algorithms can be executed on a network data structures. And each of these, then you can also have a shape files which can be stored, which is not a part of your geodatabases but as a separately. So whenever we see a shape files are not a single file, but rather than a set of multiple files which will have same name but extension will be different. So the main file SHP stores the geometrical attributes. There are then other files which stores the indexes and the attribute values, and DVF file basically stores the attribute values and so on. So these are basically the few data structures which is or data format which is available in a commercial domain as a part of your ArcGIS ISRO platform. And that was basically the view which we'll see on the front end part, but on the back it will look like a certain folders, and within that there will be a certain files with some cryptic numbers in a sequence, and that's the combinations of these files. If you properly maintain, then only you'll be able to create back the logical view in the previous as shown in the previous case, like the logical view format. There has been now a certain effort to have a kind of common data format, because the way we are having ArcGIS, similarly a lot of other companies have also started creating their own data format. So later on there has been a discussion how to allow the interoperability of different geospatial databases. So on the basis of that, the OGC or Open Geospatial Consortium has come up with certain standards for representing the different geometrical objects. So as you can see that the geometrical objects can be a point, or can be a line, or can be a surface, or and so on. So the beauty of this new OGC simple feature data format is that it can store the single polygons, or it can also store the multiple polygons and give them a common attribute. So means you can have a collections of polygon or collections of line, or there is also possibility of point or line, collect them together, and then you call it as a part of geometrical collections. And that is also been possible in if any data sets or any data structure supports the OGC standards. So the impact of that is that you can have a multi-ring buffer. So means you can create a simple collections and group them together, and you give them a common attributes like in a multi-point, or you can have multiple string, combine them together, and you can group them. That was not possible in earlier data structure like SHP or shape files. You cannot combine multiple points and give them a common values. So let's take an example of a few of these multi uh, uh, features collections representation. So as you can see, there are multiple points. You can call up them. They may be having a separate features, geometrical features, but all of them are combinedly called as a rest location. Similarly, you can have a set of paths or set of polygons combined together. So these are basically in homogeneous type collections. So as I said that you can also store a multiple or heterogeneous features as well. So you can have a point, line, polygon combined together as a part of collections, and you can create a departmental area and so on. So this is the now possible with the help of OG as a part of the OGC standard. So one of the features or one of the data structures which basically follows that is a GeoJSONs, and this is now most widely used in current geospatial domain because this allows the interoperability across the web. So simple calling and web-based call, we can have a geometrical or GeoJSON data structures which can be transmitted across. So beauty of this is this data structure is that you define a feature collections and a kind of hierarchical structures in a term of collections, objects, and their attributes, and then in a proper hierarchical format, which can be easily represented in form of text based. So that's on the left hand side. On the right hand side, you see the representation of the text, and these GeoJSON files can be easily edited in a text based processing tools like Notepad and so on. So this shows the relationship between textuals and the logical representation of the geodata sets. Then recently, the QGIS has started or taken an initiatives to make a geo package, which is an OGC compliant, basically the data format. The beauty of this particular format is that it's a SQL Lite 3 database based systems. It has a lot of properties like geometrical properties can be stored, and you can also store the images as a part of your properties of a particular features, which was not possible earlier. For example, if you're having a locations and you want to store that locations, the image or photograph which is taken at that locations, you cannot directly do it in shape files. In the shape file maximum you can attach in additional attributes and you can store its locations. But in case of geo package format, you can store the raw file itself directly as a part of attributes. The impact of that is that you you are having a single file which is able to store all the different data type and all the different attribute types which can be stored as a part of single file systems, which is greater compared to the multi-file part systems like shape files and so improving the efficiency, and it's a self-contained and cross-platform format. So nowadays the QGIS on open source GIS tools is by default they stores these information in a form of geo package cases. So it stores the vector, tile format, attributes, and so on. So all those yellow colors, whatever you see, is the core geometrical features that has to be there, and the blue colors are basically extensions. If you install the extension, you will be able to get the additional features that can be stored as a part of geo package format. So all this is possible because the SQLite databases is being used, and which stores the multi-file format as a part of blob. So you allowing it to store the any kind of data as a part of your attributes of your data sets. It also stores certain basic auxiliary informations like SRS or the spatial referencing systems, which you have seen earlier. So that also needs to be stored, and this gets stored as a part of your uh, uh, the geo package format. The KML file is the another open file format. So this stores the datasets as a part of your textual strings. Again, very similar to GeoJSONs, but only thing is like it stores the datasets in XML formats. And the other important point which have to keep in mind is that it also stores the certain annotations. Annotation means basically if any software which is going to display these features, so or any kind of KML file format, you can instruct those softwares to give specific colors to features. You can have a road with a red color and so on. So that color, style, and annotations are also being stored, and that's the beauty of this KML format, where representation layer are also bundled as a part of basic data structure, basic file format. So apart from data, it also stores the basically the representation layer as a part of your file data formats. The other most commonly used data format is, or data models are actually a netcdf file format, which is a self-contained recursive file format. So allowing it to store multi-raster, multi-vector with multi grid levels. So within the same file, you can store 9 kilometer grid, 3 kilometer grid data sets along with attributes, everything in a single file. And you can store the multi-dimensions data sets, so you can have x, y, z, time, and other dimensions can be added, and those informations can be added, dimensions can be added, and then corresponding variable and attribute values can be added as a part of the net CDF part. Only thing is like the other beauty of this netcdf file format is that apart from the regular grid, it is also possible to store the irregular grid and point also as a part of it. So netcdf is also a kind of file format which will allow you to store both raster and vector data types directly in a single file system. So these are the few examples of net CDF files. As you can see that there are X and Y. Those two are the row and column values which stores. So you have to just select those X and Y columns and corresponding attribute values in standard software. And you need to define the coordinate system. So by default, it may not have a coordinate system associated with row and columns, but you can add them and in so that can be represented in form of spatial informations. Currently, there are also big data file formats like as you can see that it's being stored as a multiple HDFS file systems. Apart from this, also there are also file formats which stores the network based or database file format also that can be stored to store all the raster and vector data models. So certain important point which we have to keep when you are maintaining and or having a spatial data set is that we need to maintain certain quality standards. So whenever that becomes an important as a part of regulations or maybe as a part of project requirements and so on, the certain data quality part has to be kept in mind. The reason for that is that when you have a multiple data sources, then there are supposed to be having certain mismatch in the positions or attribute values. For example, as you can see in these cases, the labeling of different features which is not complete in one case. So there are certain feature which is not fully covering the buildings. The other cases is that you can say is that the features which are supposed to be represented as a part of your one features may be a part of Grable and so on, that is not linked to the other features. So that due to that, there's an attribute based inconsistency arises apart from the geometrical shape and corresponding attributes. There may be also a spatial inaccuracy related to positioning or shifting, so that will result into a thematic or a spatial accuracy cases. In some cases you may be having a temporal inconsistency, so there may be a two different time period, one may data sets may have been generated, and due to that there will be a kind of discontinuity or the information missing. So we have to have some kind of historical way of representing and preserving the data quality. That also can be stored as a part of your attribute or metadata informations. So there are certain standards like ISO 211 standards which helps to tackle and take care of the technical quality datasets. So with this, we are ending this session. So if you have any questions, you can post it so that we can answer them. Thank you.